In this video, we'll go over the homework that follows the lecture 25.2, and the first part of it is dedicated to figuring out the convergence of a sequence defined by a general formula. And as always, I hope that you watched the lecture, and let's jump right into the homework. And the first question asks us to investigate the convergence of a sequence defined like this, and right away we know that visually convergence means that if we were to graph the sequence for different values of n, eventually we will hit some sort of pattern, and visually it will express itself in the form of a horizontal asymptote. So the idea is well, we can figure this out graphically very easily, and actually let me show you how. So all we have to do is to just look at this sequence. So this is my n, and this is my ln of n over n, and n goes 1, 2, 3, 4, 5. And the question is, do you see a pattern there? And maybe we can speed up the process. 100, 10,000. So it seems like things approach to 0, right? So my guess will be, without doing any work, is that the limit of this sequence is 0. However, how do we answer this question when there is no graphing device? Well, we are simply asked to find the limit of this sequence. And if such limit exists, and actually, so it's not if such limit exists, but it's the other way. If we consider a continuous function on which this sequence resides, and if such limit exists for this function, then it has to exist for this sequence. That's the theorem that I refer to as the very useful theorem. But again, this is all conditional upon us finding this limit. And if this limit exists, then that sequence converges to that. However, if that limit doesn't exist, it doesn't mean that that sequence doesn't converge. So we have to be careful here. Now, the advantage of us turning everything into x is that now we can use, we can identify the type of the limit, and we can use all the tools, all the existing tools for continuous functions. Now, by L'Hopital's rule, we can turn this ratio into the ratio of the derivatives, and the limit is clearly 0. So the answer here is 0. It looks like, again, visually, this sequence converges to what appears to be a horizontal asymptote at 0. So again, visually, and normally we wouldn't judge the convergence based on the first 10 terms, but rather based on the end behavior pattern. But in this case, it seems like it converges to 0. Another one which goes to 0. So let's just not even write anything here for it. Now this one we have, and I'll write this task right away as a limit. So we have to identify the limit of this sequence, and we can graph it, but let's say we can't graph it, so we'll just use the very useful theorem here. So we're going to convert this problem into this problem. Now we are more comfortable working with continuous functions. Again, remember this equality is conditional upon the existence of that limit. If the limit exists, then it's equal to. If the limit doesn't exist, then this inequality, this equation is meaningless. And here we're going to, let's just go with L'Hopital's rule again. It seems like we have negative infinity, so we just have infinity over infinity, although this is just a rational function with the element of radical function, but L'Hopital's rule would be the easiest way to convince us that, not to convince us, but to find the limit. And now this goes to 0 as x goes to infinity, and we end up with 16/3. In this case, we have the following pattern. Seems like everything approaches to this line over here, which would be like a kind of horizontal asymptote, and it is at -3. So we would say that the limit of this sequence is -3 as n goes to infinity. That will be the notation. Very similar problem. Here, however, we have a pattern. It seems like everything approaches to -9. So we would say the limit of this sequence as n goes to infinity is -9. Let's find the limit of cosine of 13 over n plus 14 as n goes to infinity. Again, we're going to use the very useful theorem here, and this equality is conditional upon the existence of that limit, but we're going to turn this into a continuous function. And the advantage of that is that now we have all the tools, one of which says that we can pass the limit through the continuous function. And this limit inside is equal to 0, and cosine of 0 is equal to 1. So this whole limit is equal to 1. We have a sequence. So this is an interesting example. And the problem here with using the very useful theorem is that we're not going to, it's not going to be very useful, because a function -1/13 to the power x isn't going to be a continuous function at all. So if you try to graph this function, Desmos will go crazy. And let me show you. So that probably suggests, well, any function like with a negative base, let's say, even if you just try -1 to the power x, it's not going to graph anything. The reason for that is -1 is simply 1 when x is even, but even is not defined well for real numbers. It's only defined well for natural numbers or integers, or some rational numbers, maybe, if you look at the numerator. So this is not a continuous, and therefore we cannot use the very useful theorem. Now, this kind of issue suggests that it could be, this limit may not exist, right? So, I mean, it could still exist, but it's also a sign that something's interesting going on here. So let's graph it real quick. Or let's do it without a graph real quick, just to understand the behavior. So as n goes to infinity, this component goes to 1 because it's just a rational function. Now, this simply tells you if it's plus or minus. So the whole thing will be plus 1/13 when n is odd, and it will be -1/13 when n is even. Although 1/13 is close to 0, that's going to create this type of behavior. So if this is your 1/13, this is your -1/13, it's just going to be bouncing between plus and minus 1/13, and it will never converge. So the answer is the limit does not exist. And to see it visually, let's just plot this sequence. We're going to put n over here, and we're going to put this formula over here. -1/13 to the power n times n/n+5. And we have 1, 2, 3. And what do you see here? You see kind of exactly what I said, right? It just bounces between positive and -1/13, so you have to zoom in, right, to see that difference. Actually, hold on. That's actually not true what I said, because n applies to 13. I'm sorry. So hold on. Let's go back over here. What I said is definitely true. So if 13 wasn't part of this equation, so with -1/n, see how this would have just bounced like around ±1, right? However, that 13/n actually makes a huge difference. That 13/n actually, this is what's happening, but 13/n goes to 0, so this becomes 0 plus, this becomes 0 minus. So the behavior will be actually converging. Hopefully someone watched this long enough to see that I made this mistake. So, and to show this convergence analytically, so intuitively we understand it's going to 0. Analytically, we need to use some stronger argument, and one of such good arguments could be the squeeze theorem. So let's make this argument. So we have n over n plus 5. Okay, we're going to start here. Negative 1 to the power n is always bouncing between 1 and negative 1. And when you divide it by 13 to the power n, that's going to be here, that's going to be here, then you multiply by n over n plus 5, multiply by n over n plus 5, multiply by n over n plus 5. So that's always true. And then we have a limit here as n goes to infinity, limit here as n goes to infinity, and we have limit here as n goes to infinity. Now, this is the limit that we're looking for. Now, this limit is clearly going to 0 because n over n plus 5 is 1, and you're dividing 1 by 13 to the power n. And this limit, on the other hand, is just the opposite of what we just did, so it's also going to 0. Now you have L bounded between 0 and 0, so L must be equal to 0, and this type of argument is called the squeeze theorem. So the answer here is 0, and the argument that we expect to see is the squeeze theorem. However, there are other arguments that can be made, such as this one. Well, like this is where the squeeze theorem goes in, right? So why is this limit is equal to 0? By the squeeze theorem. So they're not showing all the steps here, but we made a good argument. All right, moving on. Here, to find the limit of this sequence, we use the very useful theorem. We convert this problem into continuous function limit, and then using the L'Hopital's rule, or just by observing the pattern similar to the patterns observed in rational functions, we can find the limit, and therefore the limit of its sequence is the same, so it converges. Another one, we've seen something similar before. We're going to be using very useful theorem here, conditional upon the existence of the limit. Then we'll be passing the limit through continuous function. And the answer is 0. So the limit exists, therefore sequence converges. This is like a classic squeeze theorem. So cosine of n is bounded between 1 and negative 1 times 12, just makes it all times 12. Dividing it by n makes all of this divided by n. Throwing the limit in there doesn't change the inequality, but the limit on the right hand side is 0, the limit on the left hand side is 0. The limit in the middle is what we are looking for. So now that your limit is found to be bounded by 0 above and 0 below, the only conclusion here is that L is 0, and this type of argument is called the squeeze theorem. I have another limit. Again, it's a sequence, but we do recognize this pattern of rational functions. So immediately we see the answer is going to be 0. However, the formal argument to be made is we're going to consider the continuous function on which this sequence resides. And then we're going to notice that in this rational function 2 is less than 7. That means this rational function as x goes to infinity approaches to 0. So the answer is 0. Probably L'Hopital's rule, but only after we turn this into a continuous function. Notice how we cannot use the L'Hopital's rule here because n takes only natural number values, so you cannot take a derivative of such function because it's just not continuous. But once we convert things to x and make it a continuous function, for positive x at least, then we can use the L'Hopital's rule. And I think the idea here is that I'm actually not going to use L'Hopital's rule, but I'm just going to use the following logic. In the numerator we have exponential function, and if I keep taking derivative of it, I will keep getting exponential function. But after using the L'Hopital's rule 9 times in the denominator, since the denominator is polynomial, it will become a constant. And eventually it's just going to be infinity. But the truth is that exponential functions grow much faster than polynomials. So when you take polynomial, or rather when you take exponential function and divide it by polynomial, the answer is still infinity. So this sequence is said to diverge. Let's continue. We have the following sequence. And this one is very similar to one of the problems that we've done previously. And let me, first of all, let me simplify this. So let me pull away the sign, and let's combine the 3 in the numerator, like this 3, with the 3 to the power n. So it's going to be 3 over 3 to the power n, which is pretty much this. So this is what this sequence looks like. It's -1 to the power n over 3 to the power n minus 1. Now, to analyze its convergence, I'm going to use the squeeze theorem argument in the following way. -1 to the power n is always less than 1, and it's always greater than -1. When you divide it by 3 to the power n minus 1, nothing changes because 3 to the power n minus 1 is always positive. Now when you put the limit here, that doesn't change the inequality. However, this limit is equal to 0, this limit is equal to 0, and this limit is equal to L. So L now being bounded by zeros on top and the bottom means that L has to be equal to 0. So by the squeeze theorem we conclude that this sequence converges. Yeah, these arguments are bad. They like half arguments, and we're doing what, 13, 14, looking for the limit of a sequence, 6e to the power 2 over n minus 7. We're going to use the very useful theorem conditionally. So limit as x goes to infinity, 6e to the power 2 over x minus 7. And in this case, we just, seems like it's just a continuous function everywhere except x equals 7. So we plug in infinity in, we get e to the 0, so the answer is just 6. Alternatively, if we want to be more formal, we can pass the continuous function through the limit, or rather the limit through the continuous function, and then this is what we get. 6e to the power 0, which is 6. Another one of these rational looking expressions. So we immediately recognize the pattern. We immediately going to use that theorem. We're going to convert it to x. And now it's a rational function, and because the power of the degree of the numerator is less than the degree of the denominator, we know at infinity is equal to 0. So therefore the original sequence also converges to 0. And seems like we completed this homework in the first part. And if you have any questions, please feel free to reach out.